For over 100 years, we have known that to travel in space, we need a rocket engine that, by rapidly pushing gases in one direction, moves in the opposite direction. The faster these gases are expelled, the faster we move in the opposite direction. In short, this propulsion technique has been applied in space since the 1950s and is still the basis for the operation of modern rockets today. The high-speed gases of a rocket are produced by a chemical reaction and pushed and expanded through the rocket engine's nozzle. Since the 1950s, however, there has been thought about what might happen by putting a fission reactor inside a rocket. In those years, the idea was to place nuclear energy just about everywhere. From that idea emerged one of the first prototypes of a nuclear propulsion rocket, called NERVA, which never flew. In 1972, the project was definitively cancelled. Today, we thought of telling you in detail how a nuclear propulsion rocket works, why it is an idea that has become current again, and why there are several reasons why it could become a turning point for interplanetary travel already in the next decade. To understand how rockets work, it is essential to start with the basics of physics that govern their movement, particularly Newton's third law. For every action, there is an equal and opposite reaction. This means that if an object, in this case, a rocket, expels mass in one direction, it will be pushed in the opposite direction with a force equal to that exerted on the expelled mass. The principle on which rocket propulsion is based is thus relatively simple, but its practical application is anything but trivial. This process begins with the combustion of propellant inside the engine's combustion chamber. The propellants, typically made up of a fuel and an oxidizer, react chemically in an exothermic reaction that produces high temperature and pressure gases. These gases are then accelerated and expelled through a nozzle. To understand mathematically how a rocket works, remember only one formula, the most important and famous of rocket propulsion. This equation can simply be written as follows. Delta V equals V asterisk logarithm of the ratio between initial and final mass. Taking a very simple treatment like this, we can, for example, identify delta V as the difference in speed that we want to achieve for the rocket. V instead, also for simplicity, we can consider it as the exit speed of the exhaust gases from the rocket. The ratio, on the other hand, is precisely the ratio between the initial and final masses, once all the propellant has been burned. So far, we have therefore understood that to push a rocket, it is necessary to expel these high-speed gases, and to generate these gases a chemical combustion reaction is activated inside the engine. In rocket engines, the nozzle plays a fundamental role in determining engine efficiency, as it converts the thermal energy of the exhaust gases into kinetic energy. The shape of the nozzle, in particular, is designed to maximize the speed of the expelled gases and with it the thrust. Now, continuing with the analysis of the nuclear propulsion rocket, we must understand that the basic concepts are the same as those of traditional rocket engines. We have understood that the key to everything is to push gases through a nozzle out of the rocket and do it as quickly as possible. But what if these high-speed gases could originate in another way, instead of a chemical reaction between fuel and oxidizer? The idea that came in the 1950s, when this type of engine began to be discussed, is actually very simple. A fission reactor produces, among other things, heat. This heat can be used to heat a fluid that then expands and is accelerated by a nozzle, producing a jet of high-speed gases that push the rocket. Put like that, therefore, it also seems quite simple, but let's try to go even deeper. Let's start from the beginning. A fission reactor works thanks to the physical process of nuclear fission, a process through which the nucleus of a heavy atom, typically an isotope of uranium such as uranium-235 or plutonium such as plutonium-239, divides into two or more smaller nuclei, releasing energy and neutrons. This process is triggered when a neutron hits the nucleus of a fissile atom, causing it to split. The neutrons released can in turn be absorbed by other fissile nuclei, triggering further fission events. This process can lead to a chain reaction. Where does the gas that is heated come from? Simply, it is the fuel that is carried on board the rocket. When the fuel absorbs the heat produced by nuclear fission, it increases in temperature and, at constant pressure, would also increase in volume. According to the ideal gas law, however, inside the engine's ducts, the volume is constrained. Consequently, the increase in temperature inevitably leads to an increase in gas pressure. It is this high pressure that pushes the high-temperature gases through the nozzle, allowing them to expand and accelerate further, thus generating the thrust that moves the rocket. Let's open a small parenthesis to understand which fuel is best to use and why. Actually, they have already chosen, and they have chosen hydrogen. Hydrogen is an ideal choice even for traditional chemical propulsion. It is used, for example, by NASA's Space Launch System, along with oxygen. It is even more effective for nuclear propulsion rockets due to a series of important properties. Its lightness, first of all, being the lightest molecule in the universe, gives it a high specific impulse, which means it can generate more thrust per unit of weight compared to other propellants, thus making rockets more efficient. Additionally, its heat capacity allows it to absorb large amounts of heat without a significant increase in temperature, thus facilitating the transfer of heat from the fission reactor to the propellant itself. This is important because the heat generated by the reactor must be completely absorbed by the fuel. Hydrogen, also being extremely light, expands significantly when heated, contributing substantially to the thrust. This combination of low density and high expansion capability makes hydrogen particularly effective for propulsion. Moreover, hydrogen is a relatively abundant element and easy to produce, and it does not produce harmful emissions, though it is not easy to handle, and this is one of the reasons why it has been used very little so far. As we have described so far, a nuclear propulsion rocket might seem quite theoretical, but, as we mentioned at the beginning, in the 1960s they had already tried to build one. It was called the Nuclear Engine for Rocket Vehicle Application, known as NERVA, and it was the most advanced nuclear propulsion engine project produced to date. The idea of a rocket engine of this type was born shortly after the Manhattan Project by 3 engineers stationed at Los Alamos. The initial idea of this first group was to use nuclear microexplosions to propel a rocket, a program that was later called Project Orion and for years continued to captivate the imagination of many enthusiasts. In 1955, a further step forward was made with the birth of the Rover program, based at the Los Alamos laboratories and led by the Air Force. The objective of this program was to develop a nuclear propulsion engine as we have described so far and apply it to the production of intercontinental ballistic missiles. Already in this program, the first practical ideas that we described at the beginning of how to build a nuclear propulsion engine for rockets were envisioned. It had already been confirmed that hydrogen was the best fuel, for example, and the engine architecture began to take shape. In 1957, the launch of Sputnik 1, the first artificial satellite ever created by humanity, gave a significant boost to the American space programs, which were involved in NASA, founded in July 1958. The Rover program also came under the new space agency, which was channeled into NERVA with the goal of developing a nuclear propulsion rocket for long interplanetary journeys, particularly to Mars. The design of the NERVA engine was constructed roughly like this. Hydrogen was stored in liquid form at temperatures below 253 degrees Celsius, since there was a need to subsequently heat it up to 2,500 degrees Celsius. From these temperatures, it can be understood how difficult it is to handle it, being a very light molecule. The losses are high, and the possibilities of corrosion of the pipelines are very high. To power the fission reactor, both plutonium-239 and uranium-235 or uranium-233 were considered. In the end, uranium-235 was chosen, also because of its greater availability at the time. For the structural materials of the engine, the use of graphite or metal was evaluated, eventually opting for graphite precisely because of its resistance to high temperatures and its ability, at high temperatures, to sublime rather than melt. The control of the reactor was entrusted to control drums, coated with graphite or beryllium on one side and boron on the other, allowing very fine regulation of the fission. Indeed, by commanding the rotation of these materials around the reactor's core, the rate of fission could be precisely controlled. The variation in thrust generated by the engine was obtained by increasing the flow of hydrogen, which, being itself an effective nuclear moderator, directly influenced the rate of reactions in the reactor core. The NERVA project was developed by NASA in collaboration with the Atomic Energy Department until 1972, and its application was to be exclusively civil for space exploration missions. In this purpose also lies the main reason for its cancellation. At the end of the 1960s, the Nixon administration began cutting funds to the Apollo program, changing NASA's priorities. It would no longer focus on the conquest of the Moon and then Mars, but would concentrate on the development of low Earth orbit, first with a space station, Skylab, and then with the Space Shuttle. To these reasons were also added environmental issues and those related to the development of nuclear energy, which already in the 1970s was beginning to be less appreciated and used everywhere. The NERVA project in NASA's mid-1960s plans was supposed to be operational by the middle of the following decade and carry the first payload to Mars in 1978. Moreover, a nuclear propulsion engine based on NERVA would have been used as the engine to operate the Space Transportation System, a rocket that moved payloads and astronauts from Earth orbit to the Moon and Mars. Obviously, all of this was never realized. By 1972, at the conclusion of the NERVA project, interesting results had nonetheless been produced. The last engine was called NERVA Z Prime and was to be the final prototype before moving on to the production of usable engines. The Z Prime engine was 6.9 meters tall with a diameter of 2.8 meters and was ignited 28 times during these tests. The fission reactor produced an average thermal power of 1,137 megawatts, delivering a specific impulse of the engine of over 800 seconds. This last engine was designed to generate over 280 kilonewtons of thrust, equivalent to about 28 tons of thrust. This value may not seem high when compared, for example, with one of the most famous engines currently existing, the Raptor by SpaceX, which reaches over 2,600 kilonewtons of thrust, nearly 10 times as much. However, the NERVA engine, besides being a prototype from the 1960s, was designed to operate in space with very high efficiency values. The specific impulse that we mentioned earlier, which we can here understand as a value of engine efficiency, was over 800 seconds for NERVA, and for example, is only 350 seconds for the Raptor engine. In this aspect lies the greatest advantage of a nuclear propulsion engine. Having a higher specific impulse means that they can provide a more prolonged thrust for the same amount of propellant, and this is a very important advantage for long-duration space missions. With these engines, it is indeed possible to have the travel time to the planet Mars and reduce the risks, supplies, and costs, especially when there will be humans traveling. For this reason, the development of nuclear propulsion engines is becoming of interest again in recent years. The Artemis lunar exploration is posing great challenges to the United States and its international partners. Artemis is part of a larger NASA program called Moon to Mars. The ultimate goal of Artemis is indeed to establish a stable presence on the Moon and then facilitate exploration of the solar system. The red line crossing the logo of Artemis represents precisely the path to Mars that will open from the Moon. In addition to this, the climate emergency on Earth is, albeit slowly, bringing nuclear energy back into vogue as a source of clean energy production, which with 21st century technologies is even more effective and especially safer than 50 years ago. In this climate, nuclear propulsion has therefore returned to interest, especially at NASA. The American Space Agency, in 2023, signed an official collaboration with DARPA, another advanced technology development agency dependent on the Department of Defense. This collaboration will serve to develop the Draco project. The name of this decidedly characteristic project is an acronym that stands for Demonstration Rocket for Agile Cislunar Operations. The goal of this program is to develop a nuclear propulsion engine very similar to the one we have described in the video, which facilitates travel between low Earth orbit and the Moon. The idea of the two agencies is to use it starting from the next decade and to perform a test in low Earth orbit by 2027. NASA has been working on this project for several years, and the collaboration with DARPA will serve precisely in the design and construction phase of the rocket, to give more stability and especially to facilitate projects in which nuclear technologies are handled. Furthermore, NASA has also been working for several years on projects to develop fission reactors to be placed on the Moon, this time to produce electric power. These are micro-reactors that will be necessary if solar energy production should not be sufficient in the future. Meanwhile, China has recently announced the test of a new micro-reactor capable of producing 1.5 megawatts which could be used for nuclear propulsion. Russia, on the other hand, is working on a nuclear propulsion rocket project. But like the Chinese one, it differs fundamentally from the American project and the project we discussed today. The nuclear reactor in these two cases is not used to heat fuel, but to produce electricity with which then a very large electric motor, powered by xenon, is fed. Electric motors have already been used for many years in space. They are, for example, mounted on some satellites and have the characteristic of producing very low thrust but for very long periods of time. They are also used for some interplanetary probes, and one of the most advanced so far developed will also be mounted on the Lunar Gateway space station, which will be placed in orbit around the Moon. Let us know what you think here with a comment, and especially if you have other questions about this technology or about certain aspects we've discussed. Don't forget to subscribe to the channel.